Hello and welcome to this tutorial. This is the second and last tutorial about K-means clustering, and here we will talk about the problems and the evolution of K-means clustering. I am Abdullah Safi Chaudhry, doing my masters in data and knowledge engineering from University of Magdeburg. Alright, before I jump to the main topic, I would like to recall K-means algorithm. In step 1, we decided the value of k, which signifies the number of clusters to be generated. In step 2, we chose k random points or k random objects as centroids to work on, right? Yeah. In step 3, we assign each data point closest to its centroid points, and to decide that we used objective function, and our objective function was Euclidean distance function. In step 4, when one specific iteration was done, we placed new centroid points of each cluster, and that was the mean of all the objects of that specific cluster, and we did it for all the clusters. So we kept on iterating from step 1 to step 4 as long as the cluster members and centroids are not changing, and if they stopped changing, we can terminate the algorithm. So that was the basic K-means. Now we talk about the evolution methods, some basic evolution methods of K-means clustering. As far I can remember, I mentioned these two terms, intercluster distance and intracluster distance. So I'll go brief with these two terms in this tutorial. So in intercluster distance, this is the distance among the centroids of generated clusters. So if we have 5 clusters in our clustering scenario, then that would be the average distance among those 5 clusters, and the parameter of calculating distance of these clusters would be the centroids of the clusters, and that is expected to be maximized. Now the intracluster distance, that is about calculating distance among the data points from a centroid point of a specific cluster. So this is distance from a centroid point to all the data points of a specific cluster, right? And it happens within the cluster, and we do it for all the clusters generated by our clustering scenario or clustering algorithm, and then finally we sum the values up and we come up with one single value, and definitely that is expected to be minimized, and that indicates when the value is minimized, that means the data points are more closer to its centroid. Yeah, so this is a small and simple visualization of intracluster and intercluster distance. All right, so now I will come up with 2 important mathematical formula for intracluster and intercluster evolution. So whenever we see such kind of mathematical formula, the first thing we get confused with is the notation. So I'd like to clear out the notation first. So we start from here. The distance between O and sen I. O is a random data point in a cluster, and sen I is the centroid of a specific cluster. Yeah, and we have a summation over this distance function, and we have also a square over this distance function. So whatever value we are getting out of it, we'll square the value, and we do this calculation for all the data points in a specific cluster, that is O element of Ci. So we'll keep passing O, yeah, we'll keep passing all the data points and we'll keep calculating and summing them up, right? Yeah. So up to this part we were talking about one specific cluster, and this second summation, when we correlate this second summation with the formula, this indicates all the clusters generated by my clustering scenario or clustering algorithm. Yeah, so this is what I said earlier for intra-cluster distance, that we perform this basic thing for one cluster, then we perform same thing over all the clusters and we sum them up. Yeah, and this value E is expected to be minimized, right? And this is also denoted as sum of squared values. Okay, try to remember this term, sum of square values, and in short SSE. Yeah, now the intercluster evolution. Yeah, this is nothing but distances among centroid points of all the clusters. Yeah, or the average distance among all the cluster centroids. Yeah, so at first let's consider there are two clusters, Ci and Cj. So as we are figuring out the average distance, so here this term is included, right? Because we want to come up with the average distance. But if we talk about the distance between two clusters based on their centroids, then actually we don't need this term, because this formula is indicating distance among one data point to all the data points, one data point to all the data points. Yeah, but in reality we are not dealing with all the data points, we are just dealing with centroids. So we can terminate this part, or we can just simply put half, right? Why half? Because there will be only two data points here, right? One centroid of one cluster and the other centroid of the other cluster. Yeah, then we'll come up with one single value, and that will be the average distance between the centroid of one cluster and the centroid of the other cluster, Ci and Cj. What if we have another cluster, Ck? Then we will measure the distance from Ci to Cj, then Cj to Ck, and then Ck to Ci, and we'll add all the values and come up with one single value, and that value is expected to be maximized. And if the value is maximized, then we can say, all right, the clusters we generated, they are quite well separated from each other. All right, okay, now we'll head to one of the most important concepts of cluster validation or cluster evolution: external indices, internal indices, and relative indices. All right, now this is little hard to explain, but I'll try. Actually, just now I talked about intra-cluster distance and intercluster distance, and actually I talked about internal indices. And how is that? If you go through the formal definition used to measure the goodness of clustering structure without respect to external information. Here it is written without respect to external information. That means whatever is happening, whatever calculation we are performing, that is based on our generated cluster, that is restricted to our generated cluster. We are not using other external source or other external references to make validation of our generated cluster. All right, and by other external resource or by other external property, we mean the labels, the class labels or the target variable. Yeah, if you already know supervised learning, you should know what is class label or target variables are. All right, but let's assume as part to this tutorial series we haven't hit to the supervised learning part yet. So let's assume we don't know about supervised learning, so we have to learn about this label thing or the class label thing. Yeah, so the external indices is actually where we take help from some external resource to validate our cluster or to evaluate our clusters. All right, and then there is relative indices. This is quite simple to understand and yeah, used to compare to different clusterings or clusters. Yeah, and what is that? Maybe you have two clustering scenarios. Maybe you performed K-means over a dataset. In first scenario you generated 3 clusters, and in the second scenario you generated 5 clusters, and then you make some comparison between these two scenarios. For which scenario the intercluster distances were maximized, and for which scenario the intracluster distance was minimized. Yeah, so actually you make difference among several clustering scenario. That is the relative indices. All right, so now we will talk little more about the external indices, and if you get your understandings clear with this topic, you will get your understanding clear with this topic too. So here I'll talk about a little bit about external indices. So before I get to the basic part, I would like to put attention on this dataset. Here we can see several attributes. The first attribute, it's of no use. It has nothing to do with the calculation here because this is just index. Yeah. Then we have security, salary, DBT, reputation, and risk. So we were talking about the class label or the target variable. So let's say for this dataset, risk is the target variable. So what is the target variable? A target variable is a variable whose value is dependent on the other variables. So if you say like this, when the security level is none, the salary range is 0 to 30,000, and the DBT is very high and the reputation is bad, the value of risk is high. So class label or target variable is the variable. In supervised learning we want to predict the value of this variable. Yeah, so and definitely this value is dependent on the other independent attributes. Yeah, so note that we have 3 kinds of values here: high, low, and moderate. Now the next job would be to apply some clustering algorithm over this dataset. Now a question may arise in your mind that how you apply clustering algorithm over this categorical data. Categorical data is categorical value is something which is not numerical. Yeah, but the solution here is we have to find some good representation, good numerical representation of these categorical values. Yeah, because none of the machine learning model works with this categorical value. You need a solid representation, a solid numerical representation. So before you apply your clustering algorithm over this dataset, you have to come up with the numerical representation of these values. Yeah, and that will be discussed later when we talk about the supervised learning in larger extent. Yeah, so the step 1 would be we'll generate the clusters out of the dataset, and the number of the cluster should be the number of the target classes in our dataset. So we have high, low, and moderate as our target class values. So we want to generate 3 clusters. Yeah, as we can clearly see, we have 3 different groups here. So this will be equal to the number of clusters to be generated. Yeah. Now step 2. A cluster holding maximum number of specific class label would represent that specific class. Okay, so how to understand this step 2? Let's say in our generated clustering scenario, our first cluster has 5 members: 1, 2, 3, 4 and 5. It could be 1, 2, 3, 6, 7 or whatsoever. I'm just keeping it simple. 1, 2, 3, 4, 5. These are the members of the first generated clusters. Yeah. Now check the class label of the generated clusters. High, high, moderate, high, low. So 3 high values, 1 moderate and 1 low value. So it has higher high values in generated clusters. Yeah, in generated cluster. So this cluster will be labeled as high because it is frequent in terms of the value high, where moderate and low would be a little impurity of the cluster. Yeah. Okay, so this is what step 2 is saying. Don't get confused. If you get confused, go back to the data set and try to come up with your own description of step 2. In step 3, we have ground truth. And what is ground truth? Ground truth is just our data set. Ground truth, what it actually says, what actually the reality is, and the clustering we did, that was performed by our machine. So we have ground truth and we have the scenario our machine performed. So now we can make some good comparison between this ground truth and what our machine came up with. And in this scenario, the evaluation measures would be entropy, accuracy, etc. So entropy precisely is the impurity and accuracy is the purity. So there are more evaluation measures in this scenario, like precision, recall, and yeah, definitely we'll study it later when we study more about supervised learning. So this is accuracy, the correctly predicted objects, number of correctly predicted objects divided by all objects. Yeah. So if we go back, let's again consider the earlier example. We got one cluster having 1, 2, 3, 4, 5 members, and where the value of high was 3. Then we have 1 moderate and 1 low. So this was labeled as high, right? So in a cluster which is labeled as high, we expect all the members carrying the value for risk as high. But we have 1 moderate value and 1 low value. These are the impurity. Yeah. So these are the misclassified values. Okay. So this is what the formula is saying here. Correctly predicted objects, which was 3. Yeah. And the number of total objects in a cluster, which was 5. And the value is 0.6. So the accuracy is 0.6. So the more closer the value is to 1, the more good your generated clusters are. And yeah, more to come about this when we hit to the supervised learning part. Yeah. Now, some basic problems we face with K-means clustering. We could never decide what should be the optimal number of clusters. Very high SSE. Clusters are not very well separated. Objects within clusters are not close enough. Actually, very high SSE and number 4, they are speaking the same thing. High entropy or low accuracy, terms we just described in the previous slide, and dealing with outliers. This is the new term for you, outlier, and we'll talk about at the later part of the tutorial, at the last part of the tutorial. Yeah. Now we will solve one problem: how to find an optimal solution in terms of determining number of clusters. Yeah, the thing we always randomly initialized, that was the number of clusters, the value of k. Yeah, and now we have a way we can come up with an optimal solution which can help us to decide how many clusters we can generate out of this data set. All right, to come up with this kind of optimal solution, we have to plot this kind of graphs where in the y-axis you have the sum of squared error for different number of clusters. And how can we come up with this such kind of graphical view? This is not very complicated. You have so many available mining tools online, so yeah, just keep saving your sum of square values for different number of clusters, and then create a data set out of it and pass the data set in your mining tool. Like I really love using RapidMiner, and I believe you'd like it too. But if you have some other mining tool that you are comfortable with, that's okay. Any mining tool will do. And then you can generate this kind of visualization, and actually this optimal solution can be found visually. This is very easy. And if you see here, and yeah, this method has a name. This is elbow method. So if you want to know more, and if you want to figure out more in a mathematical context about this elbow method, just Google it, or you can ask me. You can ask to me to get some additional reading on this topic. Yeah. Now, if you see the drifts over number of clusters, to what extent the drift is happening, or to what angle the values are shifting, the values of SSE are shifting with the increasing number of clusters. Yeah. Now let's say if you keep increasing the number of clusters, yeah, you can see at some point the number of SSE is very low. Now one question is, what is the maximum number of clusters can be generated out of a data set? Let's say you have 1000 data in your data set. So the answer is you can actually form 1000 clusters out of your data set. But does that make sense? Does that really make sense? Does that really provide you the solution you are looking for? Of course not. Yeah. So increasing randomly the number of clusters would not give you an optimal solution. Many of you may think, okay, as I am increasing the number of clusters, the SSE value is getting low, but that is not realistic. You have to find one optimal point where you can figure out the solution, and you can figure out the optimal solution for the number of clusters. Yeah. Okay, so in this point you can see here the drift is quite high, the angle is quite high here. There is also the second highest angle over there. Here I believe there is no angle, there is hardly any angle. Yeah, so these are the 2 points, and the one having the highest angle, or the one having the higher extent of drift, would be the point to be selected for number of clusters. This is the optimal point. Now one question can come to your mind here, that if we have similar angles for several points in our graph, what would be the solution in that case? Well, in that case you can pick any of the 3 points. any of the random 3 points. Yeah, so picking any of the random 3 points would be optimal solution in that case. Yeah, so I want you to look at this statistical visualization and I want you to think about it all by yourself. Now, a situation where K-means likely performs badly and the concept of outlier arises. Okay, see, here you have K-means assignments. You have two clusters here. One is represented with red and two is represented with green. Now this area represents the area of the red clustering part. Yeah, now see, in this area the clusters are quite dense, and if you consider this part as a whole one cluster, then the value of the SSE will be very high, because from this point to this point, from this point to this point, from this point to this point, and actually, and this is the cross, this is the centroid. From this centroid to this point, this point, this point, they are really far. Just consider about this point, the red point here. Yeah, this is really far from the actual centroid of the cluster. So this is actually harming the health of the cluster. So there could be one possible or one useful method which could put this point away from the cluster. Yeah, and when the distance between one point and its corresponding centroid is really high, and the level of this highness is above average, we can say, okay, this point is an outlier and it should not belong to that specific cluster. Yeah, but unfortunately K-means cannot deal with outliers, because when some clustering algorithm detects an outlier, that point is completely excluded from the clustering. But in K-means, all the clusters will occupy all the points, no points will be left behind. Yeah, so that would be discussed in the next tutorial, and that will introduce to you all with a new algorithm that deals perfectly with outlier. Yeah, so that was all for today, and I'd like you to subscribe to this channel, and I'll provide this in a PDF format, the whole documentation in a PDF format in Google Drive. And thanks for your attention, thanks for being here, and I'll see you in the next time. Till then, enjoy data science.